So today we'll speak about SELinux. So just very few words about me because that's not the goal. But I've been working on Android since I think it's 2011 when Android 4.0 came out, which was Android KitKat. Began by working on virtualization, playing with Android with a VirtualBox target, and this project, which was a side personal project, ended up with being a product named Genymotion that some of you might know also, which was an alternative to the stock Google emulator. And after that, I work on many different Android projects, porting Android to different products, to different form factors, etc. So yeah, so since then I've been working mostly on Android. So today we'll speak about SELinux. So as we said during the introduction, SELinux doesn't have a good press, and yeah, doesn't most people don't like SELinux, and that's why I think it's important during the introduction of this talk that we discuss why SELinux is important. And in fact, it's really very important for the security of Android, both AOSP and AOS. So obviously, every time I say AOSP in this talk, it's the same for something for AOS. But yeah, SELinux is very important. So we'll see why it's very important. We'll see how it's managed, because SELinux, as you know, is not something specific to Android. It was done for Linux, but we will see how it's managed exactly in Android. We'll see how to debug these AVC denied things that we had seeing in the logs, but which has a lot of very important information that help us fix the policy. And then we'll see some common pitfalls and lessons that we can learn from the past, and we'll learn lessons so that we can get experience from that. And then we will finish with some QA. So first thing, why does SELinux matter? First thing is that SELinux implement what's called MAC, mandatory access control, and that's different from what's also called DAC. DAC is discretionary access control, which is basically what is used for regular Linux file permissions. You have a user, you have read, write, execute, etc. So this is very simple. Mac brings a lot of things on top of this DAC, because even the root user, which is as you know, the super user, cannot bypass the SELinux rules. So that's why it's very important. And it's important because no system is 100% secure. No code is 100% secure. So anytime the code you write, the code I write will have and has some security problems, and so can be hacked. And SELinux is here to make sure, not make sure, but make its best to limit the consequences when there's a security bug or security problem in the code. So that's why it's very important. So that's from the technical side. From the certification side, it's also very important, because for a long time SELinux is required for CTS or for Google certification. So anyone who would like to have his product certified by Google, to have the Google Play services and everything, has to implement a proper security Linux policy. SELinux is also used to implement the process isolation. That's also a very important thing in Android security. You know, it's the fact that two applications will not be able to access each other data and with each other information, etc. So that's very important. That's really part of the core Android security. And then this is usually security Linux, which is here to prevent escalation privilege abuse. So that, for example, even if there's a bug in the system that that would let a standard application gain system or root user, then SELinux would be here to again prevent the consequences and limit them. So what kind of threats can we have? So I listed here some of the threats that we have, but let's take um, another scenario perhaps that we can think of. Let's say that we have a malicious app which was either directly installed on the phone or maybe even installed from the Google Play Store, because that can happen. Let's say this malicious application exploit a kernel bug, and thanks to this kernel bug, it can gain root access. Okay, so without SELinux, with the root access, then okay, the malicious app could do whatever they want, and they could access all data from all application, even your banking application, etc. So it will be just the end of the world for your phone and all the data on it. Thanks to SELinux, in fact, even if this malicious app gains root access, the app's process will be confined to the what we call the untrusted app domain in SELinux. That means that even with root access, the app will not be able to read data from other applications, like the banking application. The app will not be able to interact with the system server binder, for example, to gain access to a private, not private, but secure API or important API. The app will not be able to interact with key store hardware via the /dev devices, for example. So that's thanks to SELinux. Okay. Another example. Let's say you have a bug in the camera where the your HAL, so which is the hardware abstraction layer, camera. You have a bug where the buffer you have share memories with other application and makes the shared memory buffer available system-wide, which is a huge security problem. That would mean that any application who knows that would be able to access the buffer from the memory. Again, thanks to SELinux, to doing what we call a mmap, so a memory map syscall, would be prevented because it would not be allowed by the SELinux application. Okay, so that just illustrates that SELinux is here to limit the consequences when any software component, an application, a service, a HAL, anything, a driver would have some bug. Then, thanks to SELinux, the consequences are limited. So this is really, really important. So now, what about the Android SELinux in Android timeline? So SELinux was introduced in Android 4.3, so that's about 12 years ago, something like that. It was introduced in what's called the permissive mode. So in permissive mode, that means that you have a policy. It is checked during the run, but it only logs the problem, and it doesn't block the process that is trying to access resources, for example, that is not allowed. This step, I think, was introduced by Google so that it was just a step, intermediary step. So just to check if everything was running correctly, and then in Android 4.0, enforcing mode was the default. Okay. It was the default, but the vendors were still they still had the capability to disable the enforcing mode, to put it back to permissive mode, and they were able to still have the Google certification. And that was finished with Android 7. From Android 7 now all devices that want to have Google certification have to be in enforcing mode, otherwise they are rejected. And with Android 10, we had a number of new features, like the never allow command, not command, but never allow, never allow command that allows the policy to list a number of things that should never be allowed by the policy. So We'll see an example later, so I will not dig into it too much. And also there was a new way to build security policy with the SECILC command that was introduced in this Android 10. So now what about the concept? So in fact, the concepts in SELinux are quite simple. The overall concept is quite simple. When you define a security Linux policy, you just have to list explicitly and extensively all resources that your process can access. Okay, it can be a file, it can be a network socket, it can be a Unix socket, it can be another talking to another process. Yeah, everything, every resources that the process will access, you have to define it, and then that means that only this will be allowed by the security Linux policy, and so anything which is out of this policy will be just rejected. Okay, so to implement that, we have different concepts. One of these is the domain. So the domain can be, for example, the type of process. It can be, yeah, usually we are talking about process. So let's say you want to add a new service to do your AOSP or AOS. You will define a new domain that will be used to yeah, to tell the system that this domain, so which will be linked to the binary which implement your service, will be allowed to do certain things. Then we have types. For example, we have here camera data file, and again, this type will be used in the rule to say that this domain can access the type. We can add attributes, which is important and interesting, so that the security Linux policy doesn't um, become too difficult to understand. Let's say you have different domains, different R, but there's a certain file, I don't know, logging file, for example, that all your HAL would has to access. Instead of saying, okay, this domain is allowed to access this file, this domain is access to load the same file, etc. You just create a new attribute. Here, for example, it's HAL domain. You will give this HAL domain attribute to the different domains that you want, and then you will just say that domain with the HAL domain attributes are allowed to access this file. It makes the security Linux policy much more clear, much clearer to read and easier to maintain. And then we have obviously the classes and the permission. So classes, for example, are the files, and the permission can be read, write, this open, execute, all of this, the type of action, in fact, that can be done. And then thanks to all this, we will be able to write rules. Would say, for example, allow HAL camera default, camera data file, write, for example, which would be allowed to write a file to this type of file. So yes, yeah. So let's say, for example, we have a deny. It's interesting just to understand how it works. So let's say you see that in your logs, in your dmessage, for example, you have an AVC denied, and it's important to be able to understand it so that you can write a good security Linux policy. So first thing we can see is that the it's a read. Okay, so that means that your process, so the process PID, you have the PID which is 4521. The name of the process is my service. Is trying to read a file which is named config.json, for example. You have the dev, which is the device on which the file is located, the INON number, and you have two very important things which are related to the domain we are talking about and the type. You have the source context and the target context. So S context is the source context, means that your process, which is named my service, is as the domain my service. Okay, that's what you define. And you see that the target context is as the type vendor configs file, and which has the type file. You see that with the T class file. So that means that uh, you probably lack. So if this access is legitimate, you lack a rule which allows the my service domain to read the vendor configs file. Um, uh, yeah, the config file type, in fact. And you can also see here with the permissive equals 0 that you are in a enforcing mode. So that means that this was blocked. If we are in a permissive mode, so obviously we would have permissive, which is equals to 1 here, and we would still have the logs in the message or the logcat, but the access would be allowed, and your process would have been allowed to read the file. So I think I have to speed up a little bit, so we'll go a little bit faster for the rest. So how Android uses SELinux? So it uses for different things. I think we discussed that a little bit already. It's used for application isolation. It's used for the HAL domains and separation. So, for example, as you know, we have many different HALs in the Android systems for each type of a device, but they don't run in the same domain. So you have the domain for your camera HAL, you have the domain for your radio HAL, etc. So that's good, because if you have a bug, a security bug in one of the HAL that you have, that means that the attacker will not be able to access data from other HAL. Same thing for the system services. Okay, system services all run in different domains, and they are not allowed to, by default, obviously, unless you write specific rules for that. The system services are not allowed to talk to each other and to read files or access data from each other. And SELinux is also used for data labeling. So that means that the type of the file depends on this location and the file system. So depending on its exact location, the file will have a different label, and that's how the security Linux policy will be able to detect if the access is allowed or not. So concerning AOSP, so yeah, obviously this is specific to AOSP. We have different policies because, as we know for some time, we have this Treble project from Google, which really tries to separate the platform, the system side, and the vendor side. So that means we have the platform policy, which is developed by Google in AOSP, that as much as possible we don't touch, because we don't want to make changes to this one. That's why you have a vendor policy, which is obviously specific to the vendor. Usually we put that in device vendor device SEPolicy, for example. This is where we put new policies, usually when you have new services about the specific HAL of the vendor, things like that. And then we can have some private policy, especially in System X that you might know. It's an extension to the system. That's where usually we will put our changes if we want to change things to the core platform. So about writing good policy, what's good to be done? Well, as I said, the type attributes is very convenient. So usually, most of the time, when we want to give new capability, we would use a type attribute instead of directly using the domains. That would allow us to have things more reusable and also more readable. Um, Concerning the rules, we want to keep them modular and especially as minimal as possible. Okay, having a rule which allows everything is not good. Is not the goal with SELinux, and will probably denied by some neverallow rules that Google has. We want to document as much as possible. This is something important. We know that for the code, but we should consider security Linux policy as code exactly. So we want to comment it, to explain it. If the rules that we have are not self-explanatory, it's good to document them and to explain exactly what we want to do. And we have some tools like SEPolicy analyze to validate the rules. What should not be done as much as possible. We have a tool which is named Audit to Allow. It's a very convenient tool. In fact, you give it the exact AVC denied that you have in the logs, and it generates a security Linux policy rule. So okay, that's nice. The problem is that we can make mistake by doing that, especially allow too many things or allow the bad things. Okay, so it's not bad to use audit to allow by itself, but what is bad, it's just to copy paste the result without trying to understand exactly what it will allow. Same thing with the wildcard. We can use wildcard, so it's can be convenient because it allows to allow a lot of things. But again, most of the time we don't really know what we do, so it's better not to use them. Something which is bad to do also, but could seems convenient again, is to disable neverallow. So the neverallow rule is a rule that we can find mainly in the platform side by Google. Google will be able to say, okay, this will never be allowed. For example, untrusted app, standard application, I don't say are never allowed to directly access the /dev/keymem, which would allow the application to access all the memory of the system. Okay. Sometimes when we build our own policy, it doesn't build because it conflicts with never allow rules. Fast fix, and very dirty fix, would be just to comment this never allow rule that we have on the platform side. It will work, but again, if this never allow rule has been created and is part of the platform, there's a reason why, and so it's much better to understand why it's never allowed and to find a different way. And another things we have not to forget is just not, please don't test only on user debug. First thing, sometimes user debug is only on permissive mode, okay? But also, especially in the platform side, policy is not exactly the same in user debug and in user mode. Okay, so that means that even if you are in enforcing mode on user debug, some rules or some access can be allowed in user debug, but not on user. So it's good to begin with user debug because it's easier to debug by default, by concept. But then it's also good to test on user bit. And another thing which is really important is please, if you define a new service, harden, whatever, write the security Linux policy at the same time you write the code. Okay, don't push it at the end, especially with big projects. I saw project where everything was developed, and then at the end they wanted to develop the security Linux policy. It was just not possible. It was just a mess, and so they ended up with putting in production a product with security Linux in permissive mode. Okay, it was not Google certified, obviously. It was not the goal, but then in the field they have products which are not in enforcing mode, and that means that this customer just removed a large number of security features from Android, and it's not good. So I will go fast on that. So please consider your policy as source code, code review, version control, CI, chest, etc. Please do that. Now, what about debug? Because this is a large part of writing the security Linux policy is about debug. So we have a number of tools here. We've first thing is to capture logs. So usually security Linux policy logs can be read from the dmessage, from the logcat. We can find them. When we have the logs, the logs and we want to have more information, so first thing, we can read it. We saw an example just before. It's quite easy to read once you understand the concepts of the domains, the types, etc. So we have audit to allow, which is here, but also audit to why, which give a more detailed information about that. The only thing is that to use audit to why, you need a compiled version of the security Linux policy, and which is not now part of the standard build of Android. It's not in the proper format for audit to why, so you have to build it by yourself and then give it to audit to why. So that's why it's not, maybe not very convenient, not always. We have the -z of PS and LS, which is very important to check the type, the file type, for example, or the domain under which a process runs. With this, you will make sure that your policy is good. For example, let's say you said that this binary should be started with this domain, with your security Linux policy. With the PS -z, we'll be able to make sure that it was enforced correctly, and that the service really runs with the good domain. And yeah, we have a specific things also about Android, which is that even if you are in permissive mode, to start a new service, you have to set the good domain to the service. So that's important, because we could think that with a security Linux policy in permissive mode, don't have to care about this policy, but we have to care when we add the new service. We have to label the service with the good domain and allow the domain to be started as a service. So yeah, so some problems that we can have, bad init-rc. If the service starts before service manager is ready, then we can have problem because it does not register. Can have problem with the file context. So the file context is the policy which tells that this path, these files in this directory are displayed. So maybe just a misspelling in the file path or something like that, or in the file context, can mislabel it. And as I said already, we can have permission allowed only on user debug and not in user. So let's have two very short case study to finish. So let's say you developed a custom vendor ARL, which is about camera. In user debug, everything works fine because it's running in a permissive mode, but in user, then it just doesn't start, in fact. So we have this file context, which says that all files in data vendor my vendor are of type vendor data file. Okay, and this is the policy of my my vendor R. Okay, so I introduce a new domain, which is HAL my vendor camera, which has the attribute HAL domain also, and I also explain that we have a new file type, which is vendor camera socket, and I allow my domain, so all my vendor camera, to write, create, and connect to this sock file. What's the problem here? It's pretty simple, but yeah, let's see first. What do we have in the logs? In the log, I have that. Okay, it's blocked. Okay, my HAL cannot access the vendor data file. But the problem is that the socket which is created doesn't have the good context. So if I just go back on my first thing, you will see that the file here I label with vendor data file. Okay, but in fact I reference a vendor camera socket, and this is where I give access to this type. So that means that I don't have the good type. Maybe I should have. Let's say I have a socket inside the data vendor, my vendor. I should have in my file context. I should add a line with data vendor, my vendor socket, for example, and affect it the type vendor camera socket, and then it will work. Okay. I have a second case study, but I will share the slide. You will see it because I'm running out of time. The number of tools I talked about during this, and So just 3-4 minutes there. Okay. Okay. So let's go with the second case study. So let's say you want to create a new system service, which is vendor, and you want to read logs from system logs. Okay. So I do everything which seems correct to me, write my service, write my security Linux policy, but then during the build, it fails. In fact, it fails with this error. Okay, and this is where we're talking about never allow. I have this never allow line, blah blah blah. It's violated by rule, and I have the rule here: allow my vendor logger system file read. In fact, what I see here is that there's a never allow rule in the platform that prevent a vendor, in fact, the vendor component, to read file from the system file, from the /system partition. Okay, and this is on purpose. This is intended because, as we know, again, with the treble project and the real separation between system and vendor, we want the system and vendor to be as independent as possible, and that's why Google, in their policy, wrote these never allow rules that prevent, that forbid the vendor components to read files from the system. So yeah, and this is the never allow that prevent that. So what can we do? So if the logs that we have are all on logs, okay, just move the logs to a vendor partition. That was a conception error, to put your logs in system logs if this is vendor logs, okay. But let's say if this is really logs that are from the system that already exist, for example, from a system component, or logs from the system by itself, and they really exist in the system partition. So what we could do then is move the service to the system X partition, because the system X partition, as the name indicates, it's a system extension, and will have the capability and the right to read files from the system partition. Okay, so that would be good. And if we cannot, for any reason, because also the problem by moving our service to the system partition, system X partition, will be that it will not be able to access resources from the vendor. Okay, so then it will be a problem. For example, it will not be able to access a specific /dev device or things like that. So a third option will be to add a proxy service, which would run on system X, for example, which would be allowed to access the log files, and then we would create a security Linux policy rule which would allow our own vendor component to talk to this proxy service and be allowed to access the log files. Okay, so that would be the different options. So if we recap the tools we talked about, so the third one we not yet talk about, but I will. When we have a AVC denied rule, we can use audit to allow. So audit to allow would just print you the corresponding security Linux policy rule that you had to write. But again, warning: don't just put this new policy without understanding what you do. Audit to Y will give you a more comprehensive result, but again, it needs compiled security Linux policy, so you might have to do this by yourself. PS-Z, LS-Z will tell you the domain of the process, the file type. Logcat, you all know Logcat will be able, it will allow you to read the logs from the system. And then when we have to debug early services where Logcat perhaps is not available or things like that, you could write no, not the Logcat, excuse me, but with the system manager is not available. The good thing is to use strace. So strace is a tool used to trace and to log all system calls, and it will help you to determine what your process is doing and where it is blocked. And log wrapper is a small wrapper that will let you send to the Logcat all the output of your process, and in this case, or the output of a trace, and then it will help you to have all this in the logcat so that you can look at it later. So this is with what we do with the log wrapper on a trace. Just one thing about service list and PS service list can be useful because you will see the list of registered services. Whether PS obviously lists you the running processes, and obviously it's not the same thing. Okay, you could have a running process, but the registration fail. So please don't mix things. Okay, it's not because your service is running that your service is correctly registered. And timing is very important, as well as security labels. Most of the time when we have problems is because we didn't put the good label ever to the domain or to the file types, etc. So this is most of the time the thing we have. So let's summarize what we said, and I hope that what was not too fast. Please treat security Linux policy as source code. This is important. Please, revision it, or code review, etc. Comment it. It's really important. If we cannot write, it's difficult at least to write 100% correct security policy from the beginning. But please try when you had a new service to write the policy and then adapt it. It's usually not a good thing to do, just to not take care about the policy, and at the end of the development just take all the AVCD denied one by one and try to adapt the policy. Usually you have an unreadable policy. The debug tools are really important. You have to understand what runs on the platform, and so you have to use all these PS, LS things, etc., to understand exactly what was implemented. And so that's